cluster. It's not nearly as dense. An anemic spiral is just a cluster spiral that's deficient in H1, not necessarily truncated, but deficient in H1. And because of this, they have a lower amount of star formation and dust. And they're relevant to the Vandenberg parallel sequence classification, where he put S0s on a sequence parallel to spirals in the Hubble tuning fork. And this, of course, bars are in here somewhere. This is just looking at the normal galaxies. But he had to have an intermediate phase between the spirals and the S0s, and he called the intermediate step anemic spirals. And A's, and so they're symbolized by the capital letter A. And this looks like an AB in this classification system. It's just one of the best known examples of this phenomenon, anemic spirals. Now, Koopman and Kenny did a really fine study of H-alpha morphologies in the Virgo cluster, environmental H-alpha morphologies, and they developed a set of star formation categories. They were based on H-alpha, but I'm illustrating them in blue light because you can still see the effects that they had. I'm not showing any graphs about it. These are just some examples of galaxies in their several categories. Now, there are environmental effects on the star-forming disks in Virgo, but some galaxies have relatively normal star formation rates, and some even have enhanced star formation rates, like the two on the upper left. But the ones on the right and below are the environmentally modified disks. They also recognized anemic spirals in the Vandenberg manner. And NGC 4548 is the galaxy illustrated under the anemic category. It's just a galaxy-wide deficiency of H1. Now, the T stands for truncated, and T/A is truncated anemic. And the example shown is NGC 4293. It has a very smooth outer disk and a very dusty inner section. Kind of looks like a bar, but it's hard to say if that's what it actually is. It looks like a bar, but it's very, very dusty. And in the bottom panel, you see a few more truncated types. These are called Virgo types. They were recognized to be unusual. You see them in the Virgo cluster, not necessarily elsewhere, but NGC 4689 on the left there, lower left, is a truncated normal. It means star formation disk is truncated, but in the part that isn't truncated, it has a relatively normal star formation rate for that kind of galaxy. NGC 4580, which is the next one. Let's see. This one. You see, is that there? That one right there. It's truncated too. It has, and this is noted in the Hubble Atlas and the Carnegie Atlas. It has two Hubble types: SA for the outer parts, SC for the inner parts. That's the way Sandage interpreted it. But it has almost no star formation outside that bright inner zone, and it's severely truncated. That's what the bracket S stands for. NGC 4569, which is this one, is similar. It has dusty star formation, a very bright center. In the inner regions, nothing going on outside. And finally, truncated compact has all the gas star formation in the center. And that's, I think that's NGC 4424. So these are some of the interesting environmental morphologies found by those authors in the Virgo cluster. Now, of course, truncation, when you look in the H1, it gets even more interesting. These are severely truncated H1 disks from this fabulous VIVA survey. VIVA, which stands for VLA Imaging of Virgo Cluster Atomic Gas. So you select the letters that you like that make the acronym that you like. And you can see some of these disks, for example, NGC 4535 is relatively normal. 4548 has galaxy-wide H1, but it's less. And then you have the others where it looks severely cut off. So truncation is very obvious as an environmental effect in the Virgo cluster. And here's a little summary of the results of VIVA, and there's the acronym again. The pictures show the severely truncated disks. Those are near the cluster center. Some of these truncations and some of these H1 disks look distorted, like there's ongoing stripping. There's H1 tails, and some are deficient, even though they're not near the center, as if they've already been there once before. And of course, there are signs of gravitational interaction. So VIVA had some very, very interesting results on environmental effects on the H1 disk. Now, the coma cluster is much more distant, but it's had some interesting results too. These pictures are from a paper by Yagi et al. 2010, and they show galaxies that are possibly in different phases of stripping in the cluster environment. And I've selected 3 of their examples based on H-alpha that show the 3 different phases that they think are going on. The upper panels show a galaxy that has disk H-alpha, and it looks like it's losing some H-alpha in these connected clouds. And the authors believe this is an early phase of stripping, and all these galaxies are probably new arrivals going into the core of the coma cluster. And then after this early phase, the disk becomes more empty of H-alpha emissions, and the clouds are strung out together on a line as they're being drawn further out. And then a later phase is the bottom phase, where you see these disconnected H-alpha clouds here. So perhaps this is different phases of stripping. Pretty interesting evidence of stripping in the coma cluster. Now, let me just say a little bit about gravitational encounter phenomena and these fun categories of rings. Now, rings are very interesting from a secular evolution point of view. I've put on the left non-catastrophic rings that you can compare with 3 classes on the right, which I would like to call catastrophic rings. Catastrophic rings formed by interactions. Non-catastrophic rings, catastrophic rings formed by external interactions. The regular rings formed by internal processes. And these rings are quite interesting. But let me just, I wanted to briefly summarize the normal rings, because I want you to realize that the huge majority of any rings you see are the ones on the left, not the ones on the right. Now, normal ring, they're sometimes called resonance ring galaxies. They are the vast majority of everything that's observed. They're thought to form by gas accumulation at resonances owing to gravity torques from bars and possibly spirals. They've been identified with resonances. Nuclear rings with the inner Lindblad resonance, inner rings with the inner 4-to-1 resonance, outer rings with the outer Lindblad resonance, and we've seen this already. Those aren't the only interpretations. Like Regan and Tubin, especially for those nuclear rings, concluded that in the presence of a strong bar, maybe some of those resonances don't exist, like the ILR might not exist. When you think about a single resonance radius, that's the epicyclic approximation. That's the weak bar approximation. But if the bar is strong, you don't just get a resonance radius, you get a resonance region, a broader region. And the concept of a resonance kind of breaks down. So Regan and Tubin prefer to call these orbit transition rings, where the orbits are changing orientation. And they've also been interpreted in another way, invariant manifolds, orbits associated, or characteristics that come out of the L1 and L2 Lagrangian points, which Leah and her co-workers have investigated in pretty great detail. So when I call these resonance ring galaxies, that is kind of an interpretive morphological term. But these are the vast majority of all rings that you see. Accretion rings are much rarer, and they are thought to be made of material, an accreted satellite. It could be a satellite disrupted around an early type galaxy like HOAG's object or IC 2006. Now, you can see the ring in HOAG's object, but let me tell you where the ring in 2006 is. It's out here, and I can see it on the screen, but I don't see it there. It's very dim. In the case of IC 2006, you can tell the ring is accreted because the gas in the ring is counter-rotating relative to the stars in the elliptical, and that's probably a sign of an encounter. And the lower galaxy, NGC 7742, in the Sauron, with Sauron data, was discovered to have counter-rotating gas in that bright ring. And there's more to the galaxy than the picture shows because it has an extended disk. So it has an accretion feature in a disk galaxy, whereas the other two have accretion features in an earlier type galaxy. And one thing you can already see for this is that if you're the naive morphologist and you just pay attention to morphology, you would classify all of those as non-barred ringed galaxies. Ordinary ringed galaxies probably depend on the presence of a bar for the ring to form. And so now you're faced with non-barred ringed galaxies. How do you explain them? Well, in this case, maybe you explain them by accretion. But by default, that's going to tell you that the properties of non-barred ringed galaxies are going to have greater dispersion because there's this mechanism for having non-barred ringed galaxies. And so non-barred ringed galaxies do have a larger dispersion in their ring properties. And those are one reason for it. Polar rings are ultra neat, interesting. They involve a disrupted satellite around the poles of a disk galaxy, usually an early type galaxy. And they were noted in the 1980s by Schweitzer et al. The idea is if a satellite is disrupted into a polar orbit, it's a more stable configuration than if it's disrupted at an angle. Because if it's disrupted at an angle, there could be differential precession, different precession rates at different radii, which will eventually cause the material in the disrupted satellite to settle into the main disk. The upper galaxy, which is hard to see, is NGC 4650A. It is a typical polar ring galaxy, and they're most easily recognized when both disks, both planes, the polar ring and the disk galaxy that it's around, are edge-on, because then it looks like the upper galaxy. But you know that out there have to be more face-on examples. The middle galaxy here, which doesn't show up too well on the screen because it's not dark enough, that's ESO 23558. It's classified as a barred spiral in the third reference catalog, but the apparent bar has a planar dust lane. No bar looks like that. No real bar looks like the bar of ESO 23558. So I'm talking about that right there. That's an edge-on galaxy. So this could be a polar ring-related system, but maybe it's not perfectly polar, but the ring, the polar feature, the high inclination feature, is not edge-on, it's face-on. And the one below is still hard to see is NGC 660. It's another one just like ESO 235. So we know that in our catalogs, there are more face-on examples of these polar rings that aren't being recognized as for what they are. Very interesting are collisional ring galaxies, which can be empty or have an offset center, like the cartwheel in the middle, or an off-center nucleus, like the one on the bottom. These are thought to be a specific type of gravitational encounter, where a small galaxy kind of crashes down the rotation axis of a larger disk galaxy and triggers a ring-shaped density wave. And you can get more than one ring. The model of Linz and Toomray in 1976 seemed to explain it fairly well, how you might get the ring. And there was a recent big catalog of collisional rings, Medora et al., 2009, and their conclusion was that if you want to identify collisional rings, there has to be a nearby companion. And you can see it in the upper one, and there are nearby companions, I think, to both of these. So they represent a specific type of gravitational encounter. Of course, gravitational interactions are more than just catastrophic rings. In the 1980s, elliptical galaxies were all the rage, and I think they still are to some extent. But people first recognized, or at least first appreciated, dust lane ellipticals, the main original example being Centaurus A, NGC 5128. We have tidal tails and bridges, M51 types, shell and ripple galaxies, and ongoing advanced mergers. I'll just say a little bit specifically about some of these. So a dust lane elliptical is just an elliptical that has an unusual dust pattern. It can be a dust lane on the minor axis of the elliptical, which is really unusual, along the major axis, or even a misaligned dust lane. And back in the old days, de Vaucouleurs, when he heard about dust lane ellipticals, he said, if an elliptical shows dust, then it's not an elliptical. Well, some dust lane ellipticals probably aren't ellipticals. Maybe they're S-zeros. And so the general view today, in this very recent paper by Kavaraj et al., 2011, is to call them dust lane early type galaxies. That way you don't force yourself to call them ellipticals. But some of them probably are ellipticals, and they're thought to be minor merger cases where a gas-rich companion has merged with an early type galaxy, a more massive E galaxy. These are minor merger type features. In the 1980s and 70s, when people still used photography, Dave Malin was an expert photographer at the Anglo-Australian Observatory, and he experimented with image enhancement with photographic plates. And I believe he may have been the first one to find these shells around ellipticals. Now, the shells are sharp-edged and sometimes alternating features, and I show a few others. Let me go back here on the lower left there, but they're harder to see. I guess it's much easier to see the negative versions of the pictures. They're very, very large. You see the elliptical is in the middle of those overexposed zones. It's a much smaller object, so these are very large features. They're interleaved in radius. They can alternate. And it's believed and this is one of the great success stories in galactic dynamics, was explaining the nature of shells, that they were remnants of a minor merger between probably a gas-poor, relatively cold disk galaxy and a massive elliptical whose potential was barely affected by this. And these shells represent the maximum excursions of disrupted stars from the encounter. When you call these features shells, you're kind of imposing something. You're imposing an interpretation on them, a 3D interpretation. And Francois Schweitzer didn't like that term. So he says, let's call them ripples instead. And so that's why I have back here shell ripple galaxies, so that you don't get too biased in a view of what exactly they are, what their shapes actually are. So he prefers ripples, but they're often called shell galaxies. Now, really interesting are the ultraluminous infrared galaxies, known as the ULIRGs. In this paper by Suris et al. In 1998, they did I think it's an HST imaging survey, and they published their very fine little atlas of high-resolution images of ULIRGs. They have very high infrared luminosities comparable to that of quasars. And if you look in the pictures, you see they're loaded with interaction. They seem to be interaction-driven objects. And these authors think the properties of these objects connect them to optical QSOs. Warps are an interesting phenomenon in galaxies. They represent, and it's very obvious in this one on the right, and I showed yesterday a possibly extreme case of this, NGC 4572, but most cases aren't nearly that obvious. But you see a relatively flat inner disk, and then a diffuse outer part that twists a little bit, and so it's kind of an integral sign, like this, like there to here, and even this one is twisted, coming down here. Up to there, NGC 4452. The origin of warps could be interactions with a small galaxy, but they don't all have small companions. But it's believed that it's possible to get these warps if the galaxies are residing in a halo that may be somewhat flattened, and if the axis of the halo, say the rotation axis of the halo, or the axis of its gravitational potential, is tipped relative to the rotation axis of the disk. And if you have such a thing, the self-gravity of the inner disk might be able to keep the disk flat, but the outer parts are more weakly bound, and they're trying to twist to be parallel to the major axis of the equatorial axis of the dark halo. So maybe these are connected with the properties of dark halos. Or I saw an article in a recent Scientific American by Leo Blitz where he argues that in the case of the Milky Way, which has a warp in the H1 layer, maybe the Magellanic Clouds are partly in conjunction, in conspiracy with the halo. They come together to cause a warp in the Milky Way. So these are. I noticed there's a poster on dark halos and warps. So it's a very important topic even now. Now, active galaxies have always been interesting from a morphological point of view. Here are Seyfert galaxies, different kinds. And this study by Hunt and Malkin, people have always been interested, what kinds of galaxies are Seyferts, and how does the morphology somehow connect to the activity? And people find that outer rings and inner outer ring combinations seem to be fairly common. And you see NGC 3081 in the top middle there is the ultimate ringed galaxy. It has almost no bulge, but it has that bright center. That's the Seyfert nucleus. And NGC 4151, the middle row in the middle panel, is also a Seyfert with, it has the Ansay at the end of the oval, and it has an outer spiral, which you can't see. And particularly interesting is how you have a very late type Seyfert, like NGC 4395. That tiny nucleus is a Seyfert nucleus. So there's quite a wide range of types of galaxies, and maybe bars are more frequent, as Johan and other studies I think have shown. But this is an important issue: the role of bars on generating this type of activity. Now, really interesting are HST images of quasars, host galaxies, which you really can't see otherwise. This is from a paper by Bacall et al., 1997. He's since deceased. And in these images, the quasar light has been mostly subtracted off so that you can see the galaxy, but there is some residual light from the quasars. And you do see a range of morphologies. That one in the middle is a relatively normal-looking R1 prime SBRSA galaxy. It looks normal. I forgot the red shift. I mean, they're not nearby. But you also see evidence of ellipticals, like let's see, this one right here, and also evidence of interactions, like that one. And the general conclusion of this paper is that interactions may trigger the quasar phenomenon, but it's really amazing that we can see the quasars quite like this. BCMs are interesting from a morphological point of view. I've already mentioned them. These are 4 examples from papers by Jim Schambert, and he classified the different categories. Remember, the CD is the supergiant Morgan D galaxy. And a D galaxy is a smooth S0-like object. And the C stands for supergiant, and it's a throwback to the old, as John has told us, the old spectral type classification of supergiant stars, where you use the term C before the spectral class. So that's what that is. Anyway, Jim Schambert classified these BCMs according to their profile shapes. There were the giant ellipticals. They had a particular profile shape. The Ds were larger and more diffuse, shallower profiles, and then the CDs had a more extended envelope. And maybe, and in a review article by Kormendy and Georgovsky, they suggested that possibly the D class wasn't important, or wasn't necessarily distinct. But the CD is still important. And when you analyze the properties of these BCMs, they're consistent with merger simulations. And that includes cannibalism, which is interesting, as a means of growing these things and explaining their envelopes. Now, the morphology of SBM galaxies, this is the LMC, could be interaction-driven. And what DeVocler and Friedman noticed in a 1972 article was that these often come in pairs. Now, I haven't looked for the pairing of all the SBMs in the S4G survey, but in some of the most prominent cases, they come in pairs. Now, let me introduce you to counterwinding spirals. These are extremely rare morphologies. I should have told people when they were doing the Galaxy Zoo project to look for these. But there's only a handful of examples. A counterwinding spiral is a relatively normal-looking spiral galaxy that has two sets of spiral arms. One set of arms opening in one direction and another set of arms opening in the other direction. And this is NGC 4622, the first genuine case noticed. Now, how is this noticed? A professor, as far as I know, this is the story behind it, Professor Gene Bird, University of Alabama, was using Frank Hsu's astronomy textbook. And Frank Hsu was one of the co-authors of the Lin-Hsu density wave theory. And in the book, this galaxy was presented as an example of a density wave spiral. But as a typical density wave spiral, when it is very much not typical, it's got something inside those two arms that opens outward in the opposite direction. It's a counterwinding spiral. And you can have fun with a galaxy like this with Fourier analysis. You can calculate Fourier images. And you'll notice the m equals 1 image has a single arm opening counterclockwise, whereas the m equals 2 image has two arms opening counterclockwise. And so you can see clearly that there's two sets of spiral arms and that they don't overlap. They have different radial domains. Now, if you assume that everything in this galaxy is turning the same way, then at least one of these spiral arms is a genuine leading spiral arm. And the question is, which one? And, well, it's hard to see. There's a color image at the upper left, an HST color image of this galaxy. How do you figure out the sense of winding of the spiral arms? Well, the first thing you need is a velocity field. And at lower right, I showed the velocity field, Fabry-Perot velocity field of NGC 4622. And it's color-coded such that the red parts are receding and the blue parts are approaching. And so the north side of the galaxy is receding. But that's not sufficient information to tell you which way the galaxy is turning, because that's what you want to know. Is it turning clockwise or is it turning counterclockwise? And you have to use the near side, far side dust asymmetry approach. So what you have to imagine is that we're looking at it from this area here, and this part of the galaxy is tipped towards us, and that part is tipped away. And on the side tipped towards us, you'll notice that most of the bulge light is behind the dust layer. See here? Whereas on the side tipped away, most of the bulge light is in front of the dust layer. And this galaxy has a very significant bulge, but it's only tilted 20 degrees, so how could this method work? Well, this is HST resolution, and it has a big bulge. And you'll notice in this color index map here, which is V minus I, you see thin dust lanes on this side of the line of nodes, one side of the line of nodes. And there's even a little dust lane in the middle. I don't know if you can see it, but there's a little edge-on dust lane right there in the center, but most of the dust is there. Now, this galaxy is at low galactic latitude. You have to wonder, maybe this is foreground galactic dust, but it looks too much like it follows the structure of the galaxy. So the suggestion is that the left side, the east side, is the near side of this galaxy. And so if that side is the near side, it means you're looking at the galaxy on this side here. In order for the north side to be moving away, it's got to be turning clockwise. And then you have your green circle moment where things don't work out the way you expect. That makes the two outer arms of that galaxy leading arms. You see how bright they are? The two outer arms are leading. Well, that's a difficult thing to accept. And this is in terms of spiral structure theory. This is how leading arms are. This is what leading arms are supposed to do. If you have a leading wave packet emanating from, say, near the center of a galaxy, it propagates outward, and as it propagates outward, it starts to. If it starts out as a very wrapped leading wave packet, as it propagates outward, it unwinds a little bit, and then it reaches a barrier towards co-rotation, and it reflects off the barriers back towards the center and gets more open as it does. And when it reaches the center, it swings. It swings from a leading arm spiral to a trailing arm spiral. And due to a conspiracy between epicyclic motions and the way the arm is swinging, you can get stars staying near the arm as it swings, and that enhances its self-gravity, and you get a considerable amplification of the trailing wave over the original leading wave, and so you have swing amplification. So if you see strong spiral arms, it just seems like it would have to be trailing arms, because they're the ones that get amplified, not the leading arms. So it's hard to understand this galaxy. And yet, if you use the standard method to determine the sense of winding of the arms, it's the outer arms that are leading. Now, there is another example that may help us appreciate it. Here's another galaxy. Now, NGC 4622 was in a cluster environment, and you could imagine, perhaps in that case, here, in this case, there was an encounter. After all, there's a little dust lane in the middle. Maybe it absorbed something, and maybe that's the trail of an absorbed galaxy, and it's just confusing us into thinking that that's the near side. Maybe it's just a coincidence. Now, here's a galaxy, not in a cluster environment, very obscure, ESO 29727. I found it when I was doing the catalog of southern ringed galaxies. After examining hundreds and hundreds, maybe thousands of ringed galaxies, that's the only one I found that was like this. It has a bright inner arm that's opening opposite two to three outer arms. And when you use this identical method, it's more inclined than 4622. If you use the identical method, you get that the inner arm is leading, and maybe theoretically that's more satisfying. But in this case, it's the inner arm that's more prominent than those two outer arms. And there are other examples. I've already shown NGC 3124, where you have a leading arm bar in the side of a ring. Another one is NGC 6902. And in a recent study of Vaisanen et al., 2008, found what they think are two leading arms, but not in a counter-winding spiral. They're most obvious in the counter-winding types. But spiral structure theory definitely favors trailing arms. They're the only types that are thought to be able to transport angular momentum outward to help maintain and generate the waves. So what causes it? Well, it could be an interaction. And as I've explained, there's an issue with swing amplification on this. Now, let me just say, too, that NGC 4622 is kind of a non-barred ringed galaxy. Another non-barred ringed galaxy, but not an accretion ring type galaxy. You see the ring is quite bright. It's in parts. It's more of a pseudo-ring. And as a class, non-barred ring galaxies are rather interesting. This is NGC 7217. On the left is a blue light image. On the right is a B-I color index map. And at the bottom is a very deep image of NGC 7217. Now, it's inclined about 35 degrees, but at very low levels, it's round, as if it's embedded in a very significant amount of bulge. And people discovered counter-rotating, some fraction of counter-rotating stars in this galaxy that suggested it may have had an episode of a bar-type episode, but it has such a massive bulge that maybe it can't hold the bar. But it has a ring, and a lot of the gas is in that outer ring, which is very, very interesting. It sort of reminds me of the sombrero looked at face on. Other non-barred ringed galaxies make you wonder whether we're seeing secular evolution or the products of secular evolution, like NGC 7702 there. It has a very bright stellar ring, and in the insert there, you see that there's an outer ring as well. And in the middle, there's a nuclear bar, but there's a primary bar. Now, either the ring itself is a primary oval, or else this galaxy has somehow lost its bar. Nature has run its course, and it's got that little nuclear bar there to tell us what it did to its primary bar, because nuclear bars don't align with primary bars necessarily and support the orbits there. And here you have a large nuclear ring on the bottom in a non-barred galaxy. How did that form? And then the bullseye galaxy, NGC 7187, has a little oval. Does that explain the ring? It's a star-forming feature, and you see in the inset it has another ring. It hasn't been really investigated what caused that structure. High redshift galaxy morphology is very, very interesting. These are some of the categories that people find they don't necessarily fit into the Hubble system. Sometimes they do. You have ordinary spirals and ellipticals on the upper left there. But the bulk of them don't look like ordinary morphologies. And a lot of these categories are due to the Almagreens, Vandenberg, Cowie et al. But you see clump clusters, just groups of large clumps. You see chains of clumps. You see bent chains. You see rings which are not resonance rings. They're probably catastrophic rings. Things that might be mergers. And there's a general irregular shape. And as you go to high redshift, there's a greater abundance of those irregular shapes. And if you want to know when did the Hubble sequence fall into place, you probably define it as between a redshift of 0.5 and 1. These are the bulk of high redshift morphologies, are these strange irregular shapes. So that's an interesting aspect of high redshift morphology. Giant low surface brightness galaxies are beyond belief. Malin 1 up at upper left there was the first one discovered by Dave Malin, who probably did the photography. He was such an expert at photography. And I couldn't find a decent picture other than that picture of Malin 1. But it's a huge background object to the Virgo cluster. And Bothan and co-workers looked for these and came up with a number more. They happen to be galaxies with relatively normal-looking bulges and some inner disk, but very extended outer disks of low surface brightness and low gas surface density. And they're an interesting and important class of objects. And here I just show 3 of them. Now I also show here another one that's not a giant low surface brightness galaxy, just merely a big one. It's this ghost to the right of this big spiral, NGC 7531. You can barely see the ghost. It's 2/3 the size of that spiral. And I saw a recent study, and I believe it is related to the spiral. It's an interacting system, and it's probably a disrupted lower mass galaxy that came too close to the big spiral. But it's kind of a large low surface brightness galaxy. So these may be, these are certainly thought to be important contributors to the galaxy population. They're just it's hard to see their structure. Ultraviolet galaxy morphology is also very interesting. At ultraviolet wavelengths, you mostly see young stars. And as Rainier talked about, the massive early type galaxies show the UV upturn. That may be, and he listed other possibilities, that may be due to hot horizontal branch stars. You can use the UV flux. We've already heard about star formation indicators. That this is thought to be one. And the UV flux is thought to be absorbed by the dust and then re-emitted in the infrared. And the Galaxy Evolution Explorer provided a huge database of UV images. And one of the most interesting ones is M51. And in M51, you see that the spiral just booms in the UV. It's not just the youngest stars you see. There's stars, hot stars younger than 10 to the 8th years. There's a background in the far UV image. And you see, a lot of the blobs in the arms, but the thing that's conspicuously missing is the companion in that far UV picture. It must not have a UV upturn, because if it did, I think you'd see it in that far UV image. But NGC 5195 does not seem to have the UV upturn. And so all you see is the spiral in that UV image. And here's a small set of UV images of different galaxy types. NGC 1317, 4314, they're just two early type galaxies. Mostly what you see is a star-forming nuclear ring. And then you get towards later and later spirals. And one of the most important discoveries of galaxies is this galaxy here, NGC 4625. It's a diminutive Devocalurian SBM galaxy. And that part of it is that little bright spot in the middle. The rest of that stuff nobody knew was there. This galaxy was known mainly for this part, but not this other stuff. And this is the discovery of extended UV disks. And in this paper by Gil de Paz, they suggest the galaxy is currently forming most of its stars. So it's a very interesting finding from GALEX. NGC 5253 has an irregular galaxy in the middle of a smoother-looking background galaxy, which you still see in the near UV because it has an early type spectrum, I believe. And it's characteristic of what Sandage called an amorphous galaxy. The near UV morphology of a galaxy like M83 compares very favorably with an H-alpha image on the right, but you see more in the UV image because there's a background. There's a slightly older background disk. Now, here's the morphology of the interstellar medium, which is also interesting. The FINS survey, the H1 survey of nearby galaxies, is a really terrific H1 survey. High-resolution maps of a significant number of nearby bright galaxies. And I selected 8 here to show some of the interesting features. What do we see in these images? We see extended H1 disks, as in this galaxy here, with spiral structure. You have H1 holes, as in this one. You see large gaseous rings, as in this one, and pseudo rings. Smaller rings, as in this one. And down here, you see a galaxy that's full of holes in its H1 distribution. Those are thought to be supernova-blown holes in a small galaxy, because that's a dwarf. And sometimes you see huge H1 to optical sizes, as in DDO 154. So this is the morphology of typical galaxies. Also, I wanted to point out this one, NGC 4736, John's favorite galaxy. It's hard to see in that picture, but the optical picture that I'm showing, that it has a very big outer ring. But in the H1, it's not a ring at all. It's just a spiral. So that's an interesting aspect of that one. The BEMA, the Berkeley, Illinois, Maryland survey of nearby galaxies produced these CO maps of a significant number of galaxies. And this is also important. This is another part of the interstellar medium. And what we see in these images, we see spiral arms, as in NGC 628. We see scattered giant molecular clouds here, molecular rings, molecular bars, molecular gas along primary bars, and here's another one with a hole and a molecular ring. So we do see a variety of features in the CO morphology. And here's another aspect of the ISM, 8-micron IRAC images. They show the warm dust associated with spiral arms. And to the left, I've put a B-I color index map. This 8-micron image is due to Wilner et al. 2004. But in the B-I map, you can tell the near side of the galaxy. You see, here's the dust preferentially extinguishing this side. And you don't see it so much on the other side, so that must be the near side of the galaxy. And you can see those dust lanes even in the 8-micron image, but you don't see the near side, far side effect because you're not seeing stars in the 8-micron image, whereas in the B-I map, you're looking through the starlight of the bulge. So here you get, so with the 8 microns, you get a kind of a complete view of the dusty interstellar medium for those temperatures for galaxies. Now, I want to talk about the Sloan Digital Sky Survey. To me, it's astonishing the influence this project has had. It's just beyond belief what a great project this was. This is the ultimate morphological database. And now it's not just morphology. There's photometry, spectroscopy for more than 1 million galaxies. I mean, and it's only a part of the sky. If they do this for the rest of the sky, we're going to be swimming for decades in the data from a project like this. It's just beyond belief. It opened up, it kind of opened up the new era of these huge digital online extragalactic databases. And one of its terrific advantages is the advent of large-scale color imagery, where you can see some of the things we needed numbers to appreciate before. So I want to talk a little bit about that. And one of the things that's fun is the morphology color relation. Now, in the past, you would have those diagrams at the upper left. These are mean colors versus Hubble type, coded on the RC3 numerical scale, where t equals -5 on the left are ellipticals, and t equals 10 on the right of those plots are Magellanic irregulars, and all the other types are in between. And you have B minus V, U minus B, V minus R, V minus I, and B, I think it's B minus H is the lower left color plot. That's this one here. And here you see the morphology color relation directly. But there's another way to look at this that SDSS was very, very useful. And I'm only using a schematic I found on Wikipedia because I thought it was sufficient for what I wanted to say. This here is the same as those plots I just showed you, the mean color versus type. But instead of being based on a few hundred or maybe 1,000 galaxies, this is based on many, many thousands of galaxies. And you put the it's kind of an HR diagram for galaxies. It's been the subject of a lot of research. You have the absolute R magnitude on the x-axis and the U minus R color. So that's the standard. Now it's the standard galaxy color magnitude diagram, and it shows 3 parts. One part is called the red sequence, and in it you see a correlation between absolute magnitude and color. That was once the rage for the distance scale. Back in the 1980s, when people were trying to find ways to get distances to galaxies, the color magnitude relation provided an independent index of absolute magnitude that you could use to get distances to galaxies. So that correlation has been known for many years. And it applied to E and S0 galaxies, and I think it was even carried to early type spirals. But here we see it with hundreds, in this kind of diagram, we see it with many, many more galaxies. And then, remember, they're all red, and so those curves at the top there, they start out with all being red. We're just seeing this, so this is the reds. These are red sequence galaxies, and these here at these peaks, they're red sequence galaxies. But if you go to the blue end here, these areas here, that's where you run into the blue cloud, which includes the intermediate to late type spirals. And in between, I should say that based on this kind of thing, if you plot the distribution of colors, it's bimodal. One of the modes is the red sequence, one is the blue, and then there's a dip between them, which is known as the green valley. And in this dip, you find redder early type spirals. And people are interested in possibly the evolution of galaxies from the blue cloud to the red sequence as they quench their star formation, as they either use up their gas or lose it. So this is a very important thing that came out of Sloan, I think. One thing you can do is have nice color images of elliptical galaxies. I'm getting back to John's views of some of ellipticals. A compact elliptical like NGC 4486b is probably a low luminosity counterpart to some of these larger ellipticals. And here are some compact ellipticals in color. And as I said on the first day, that these dwarf E's and S0s, these are probably environmentally driven morphologies. And they're found in the Virgo cluster. and they were probably the galaxies that have been modified, late-type galaxies that have been modified by the cluster environment. So now they're known as spheroidals. Blue compact dwarf galaxies have been an interesting class. They're small, they're high surface brightness, probably experiencing a strong starburst. I show 4 examples here, and from this paper by Gil de Paz, these are some of the average properties of objects that we call blue compact dwarfs. Now, there's one blue compact dwarf that's especially been generating a lot of interest in recent years. One's Wiki 18. It's a horrible-looking mess. When it was first studied, it was thought to have only young stars, so it was thought to be a real young galaxy. But with a deeper color magnitude diagram, there is an old component. I think it's right there. And so it's not a young galaxy. It's a galaxy dominated significantly by young stars and lots of supernova-driven bubbles. So that's an interesting BCD. Another interesting new class is ultra-compact dwarfs, very compact spike. Luminosities comparable to BE galaxies. There's the absolute magnitude range. Brighter than the Milky Way globular cluster, fainter than the compact E. And at least one interpretation of them is that they're the threshed nuclei of DEN galaxies that I guess have been stripped of their outer parts, and all that's left is just the nucleus. And that diagram there, the red spots show the distribution of these UCDs, ultra compact dwarfs, in the Fornax cluster. So they're of considerable interest in recent studies. Isolated galaxies. I thought it was really cool to use the SDSS to collect some pictures of what are thought to be isolated galaxies. The isolated galaxies were selected from a catalog by Kent of the catalog of isolated galaxies. How do you determine that they're isolated? Well, you have to do a nearest neighbor type analysis, and I think they're considered to be isolated if they feel that there's no evidence that a major galaxy has passed near these galaxies within the last 3 gig years. And they're astonishingly beautiful galaxies. Now, do these galaxies support the idea that spiral structure can arise spontaneously? I mean, they don't necessarily have companions, and yet they look like this. So it's an interesting question. What do these have to say about spiral density waves? So I thought that was interesting. Now, Galaxy Zoo. This is one of the things that was spawned by the Sloan Digital Sky Survey. We're professional astronomers. We don't have a lot of time to look at 1 million galaxies. I would love to do it because I think I would enjoy it. But my hair is already gray. What do I want to be doing in the next 10 years? It took me 10 years to produce the catalog of Southern Ring galaxies. Why did it take so long? First of all, I had to find the galaxy, so I had to look at all these charts on a light table and use my magnifying glass. And when I found a ring galaxy, I had to take the magnifier and measure the major and minor axis of the rings. I had to put the ruler along the bar-axis, the ruler along the major axis of the ring. I had to measure that. It takes a long time to do that, apart from the fact that you have to... And then once you find the galaxies, you have to get the coordinates, and this was in the 1980s. And it takes time to do that. Now, it's faster. It might be faster with this, because I might do it a different way if I had the Sloan survey. But still, we're talking about many, many more galaxies, and people just don't have the time to look at them. So... there were people like Kevin Shawinski who wanted to look at large numbers of Sloan galaxies in order to find elliptical galaxies that were blue and not red because he was interested in them. And he looked at 50,000. He could very well be the person who has classified visually the most galaxies of anybody, because I haven't done that. I mean, there are 4,000 galaxies in the catalog of Southern Ring galaxies, not 50,000. But anyway, so he was the he and Chris Lintott spearheaded the Galaxy Zoo project. Their problem was how to classify 1 million galaxies to allow people to do morphological selections of star-forming galaxies that look like, that are unusual for their type. And so they decided to outsource it to the internet and ask volunteers. And you know what? Considering that the public is presumably paying for this project, what a great way to engage the public. I just think it's wonderful. It's a beautiful idea, and I looked at all the papers that have come out of Galaxy Zoo. It's just dozens and dozens. It's going on and on. There's all sorts of things that this leads to. I'm only going to talk about a little bit. They did Galaxy Zoo, at first Galaxy Zoo 1 asked people questions. What they do is they have an interface where you bring up a picture of a galaxy and you can answer with buttons a few questions. You know, does it have a bar? Is there something peculiar about it? Does it have a ring? And people would answer that, and people who are not scientists could submit their interpretations. And then the professional astronomers would take that data and find a way to average it. And they would do weighted averages because they could figure out people who were a little bit more conscientious about how they were doing it, who were more consistent with the means they would give, who were more consistent, and they would give them higher weight. And there were certainly dedicated people doing this. So this is a wonderful way to engage the public in science. I just really like it. The first thing was Galaxy Zoo 1, and these are just a summary of some of the things that were found in Galaxy Zoo 1. The decoupling of color and morphology, and now they can say that 80% of galaxies follow their usual color morphology positions. Red early types and blue late types, but now they could find the galaxies would not follow their usual color positions. There's possibility, looking at the green valley, that blue to red is faster than from spiral to early type. They found that local fraction of mergers. They even asked people whether the galaxy was a spiral this way or a spiral the other way, looking for a preferred rotation direction, and none was found. And there's issues. There were papers about black hole growth. Here are some pictures. They're pretty hard to see. They studied AGNs, but one of the things about this project and this is what motivates the public, I think, was the potential for discovery. I mean, you were looking at things people hadn't looked at, and so even for a non-scientist, there's a potential for discovering something interesting. And there were some interesting things that were discovered. Green peas. You see that left frame there? There's a little green spot in the middle. It's called a green pea. It turns out to be a particular type of compact galaxy with a lot of O3 emission in the spectrum. They're fairly compact, and they have some characteristics in common with other compact classes of galaxies. There were red and blue spirals. Red and blue spirals. The red spirals are the ones you found probably in the Green Valley. Masters et al. Did a study of these red spirals, and you notice the two spirals I showed there, the red and the blue, look pretty much the same, except that one is red and one is blue. And they found that stronger bars existed in the redder spirals and suggested that maybe the bar was suppressing the star formation in that case. But, these kinds of things remind me of this. When I was doing the CSRG, I had to ask, why did I sit down and do that? It just took so long. What was the motivation for doing something like that? Well, first of all, I was interested in the shapes of rings, but the other thing was, it was the one out of every 50 to 200 objects that I thought were interesting. There was always something. There was a potential for seeing something new by doing a survey. And that was true here. But there's also the 1 in a million objects that's interesting that you can find in a survey. And that object is Hanny's forewarp. Let me talk about that. Hanny Van Arkel was one of these zooites. She was a zooite, and she was doing what all the other zooites do. She goes to the Galaxy Zoo, and she starts the process. She's presented with a picture, and she presses the buttons and classifies it. But if they see something interesting, they're encouraged to post the interesting object on a forum so other people can see it. Now, she wasn't the first one to post the picture of the forewarp, but she was the first one to bring it to the attention of the professionals. And so, in gratitude to her, they named it after her. It's known as Hani's object. And it turns out to be rather unusual. And this is an HST picture on the left. It's thought to be tidal debris. Like there is a companion galaxy, IC 2497. It may have had, there was an encounter in the past. Hani's forewarp is tidal debris. The encounter triggered inflow onto a black hole in the center, and there was a brief quasar period, and we're seeing the light echo of that period. And the quasar phase is over in the spiral, but the light echo is still seen. And this is described in a paper by Lintott et al. And these pictures to the right, it's hard to see in this lighting, but it kind of shows the geometry of what may have happened to produce the forewarp. And now there are other searches for Hani's forewarp type objects, because it may not be the only one. It may not be the only one. And another thing with Galaxy Zoo is if you have a particular type of thing you'd like them to look at, like Bill Keel wanted overlapping galaxy pairs to do studies of the dust, post on the forum and tell the citizen scientists to keep their eyes out for this. And you can get a nice list of objects to study. If you look at the forum, there's all sorts of things that you can find. It's well worth looking at. There are ring galaxy threads. There are spiral threads, barred galaxy threads. You look through those, you're bound to see something interesting. And that's where they put their one out of so many that are interesting, the ones that kept me going in the CSRG. It's really amazing what people have done. Now, these are just a few. I just had a few other things to talk about with regard to Galaxy Zoo projects. They wanted, for example, Skibba et al. Wanted to use the bars in Galaxy Zoo, and that was one of the questions. And so this set of pictures here shows morphology by vote. All the ones on the top have an average classification with no bar, and the ones on the bottom have an average classification with some bar. And the others are in between, and they use that to select the ones that they think are really barred. And then they examine the environments of these galaxies, and also bulge-dominated ones, and found that the barred galaxies were in denser environments. So it's an interesting study. Another thing is people were asked to note merger, interacting systems, and people have looked for tidal dwarfs in these merging, or tidal dwarf candidates in these merging systems. This is a paper by Kavaraj et al., 2011. This could go on and on. There are other large surveys. Of course, there's the Hubble archives. And Galaxy Zoo has carried the idea of citizen science beyond the Sloan survey to the Hubble archives and to other archives. Because there's a huge database of morphology in the Hubble archives. There are big, deep surveys as well. And the amount of information that we have to work with is just going to skyrocket, especially when other surveys or the James Webb Space Telescope goes up. So here are my conclusions after all this. What I find interesting is that in 1990, classical morphology was viewed with disdain. I'm up there giving a talk in Sant'Agata, Italy, and I talk about classical morphology, and someone gets up and says, it's no longer relevant. And so people should be quantifying classification, classifying by subsystems. Now, people are quantifying classification. That's always a good thing to do. But qualitative morphology is still relevant today, and there's a huge database of material to work with. The Hubble tuning fork is being seriously modified. S-zeros have probably been in the wrong place. Maybe now we've found the right place for them. And dwarf early types, the study of dwarf early types has led to the resurrection of parallel sequence classification Cormany and Bender worked on. And the quality of the digital images has allowed the old classification systems to be modified and reveal other features that we may have ignored before, like nuclear rings and nuclear bars, but now that we're interested in. And infrared classification is now possible. Early type galaxies continue to be the focus of a great deal of research. They're very relevant to evolution, secular evolution. In S0 galaxies, there's loads of things that could be related to secular evolution. But the S4G provides the opportunity to study the properties of extreme late type galaxies because there aren't very many early types in that survey. Now, all these big imaging surveys, SDSL, Hubble Archives, deep surveys, Cosmos, GOODS, HDF, HGF have a lot of morphological information. So, to quote Chi and Peng, which I had in my first talk, the processes of secular evolution and formative evolution lie in the fine details of galaxy morphology, and I think we'll have an awful lot of fun in the coming years trying to interpret those details. Thank you. Questions?
Maybe this is the time for a discussion like this. I gave a public talk in Granada last week trying to argue that the difference between elliptical galaxies and spiral galaxies, it's much smaller now than in reality than when people started the classification, just because people know much about it. So now we still have this classification system where there's two big classes, E and S. And, well, I've given a number of things which are in both. Say, the little disks in all these systems. The bulges are like ellipticals, nuclear clusters, outer parts are similar, halos. So they're all, I think I could even probably say that the differences between large galaxies as a whole and small galaxies, dwarfs, is larger than the difference between ellipticals and spirals. Wouldn't it be time to think about a new system, but then which is which is not that much affected by the classical diagram, which then biases the way that people that don't know all these details look
in the early 90s, there were a number of papers that tried to get away from those old systems as well, but the old systems linger because we went to higher redshift. Our databases increase, and I think they're still useful, and it's nice to have a connection with history, but that doesn't mean we shouldn't look for a new way. I agree with that. Like for example, I'm looking at the S4G data with Hubble, and it's in here. How do I get rid of it and look at it fresh, or find some other way? We have to use other approaches, but certainly I agree that it's worth looking. Yes.
I have a question.
Yes.
Both you and Ranier spoke about UV.
The UV, yes.
Yes, and with Galax and HSD getting out of operation eventually. What happens to UV astronomy?
Gee, UV astronomy could use higher resolution.
You can't do it from the ground.
Pardon?
You cannot do it from the ground.
Yes, I know. You need higher resolution from space, which means we have to send up another space observatory. Even infrared needs higher resolution because S4G has their drizzled pixels are 0.75 arc seconds. They're still pretty big. I don't know. It depends on what sorts of future space missions come out. But the James Webb Space Telescope, I think the funding was almost canceled recently. As far as I know, it hasn't been cut. But if it goes up, that will help, in some respects. But you're right. The UV needs higher resolution. So there's more to be learned as we open up a new window. If we open up a new window or we improve resolution, we're bound to discover new things. So for progress, those things have to be done. So I don't know.
Yeah. But something else. What do you think about new projects like Euclid?
Which one?
Euclid.
What is that?
It's a space mission by ESA. I think it's launched in 2019 or so. 15,000 square degrees. Magnitude 24.5 or so. 0.1 arc second pixels.
Wow. Well, 2019? I hope the budget will support it at the time. I wouldn't make any predictions about things like that in the future, but it'll be. Of course, I hope it'll go. Well.
So I really don't like how he disagrees with Rainier a lot, and with the Ceylon team in general. But there is a very fundamental difference of opinion between, I guess, me and them, and between the whole Hubble sequence and their approach to things. And that fundamental thing that Hubble recognized correctly, and Alan Sandage expressed this very well in one of the atlases and said it was a part of the fundamental genius of Hubble that he recognized what features morphologically will turn out to be physically important. And the single most important thing that he differentiated was between galaxies that are flat and that turn out to be rotating. He didn't know that. He knew they were flat. Galaxies that are flat and galaxies that are round. And we now know enormously more about those two things than we did then. But the galaxies that are round are supported much more by random motions. Galaxies that are round, we now understand, were formed by major mergers violently in short time scale, episodic formation events, whereas the disks were formed very slowly, very gently, always kind of not so far from equilibrium, gradually accreting cold stuff, right? There are people now that work on cold flows, talk about cold flows a lot. There's an enormous difference in the formation processes between the flat things and the round things. There's an enormous difference in the structural properties and the way the galaxies look. If you look at a big elliptical edge on, it looks E4. If you look at a disk edge on, it's E10. It's got a 10-to-1 axial ratio. There is a really very fundamental difference between disks and their formation histories and ellipticals and bulges in their formation histories. And when there's both in one galaxy, I'm sorry that I have to disagree with the Sauron team, you've got to separate them and study them separately, or you're going to find a continuity between them and fool yourself into thinking that disks are just a little bit at one extreme and ellipticals are a little bit at the other extreme of a continuum. And it isn't so. And I'll try and talk about that a bit later, but it's really quite a fundamental difference between the way many people who have been doing decompositions for the last 30 or 40 years view the way you study galaxies and the way the Sauron team does, who do not want to separate bulges from disks, want to always study them together. And I don't understand that approach.
I wonder about the differences between the star formation of different types of ring galaxies.
Ring galaxies?
Yeah. Is there a pattern? You talk about these different types of ring galaxies.
Oh, you mean the collisional? I see. You mean the resonance, accretion, polar, and collisional?
Yeah.
In general, as far as accretion, polar rings, and I guess collisional rings, there is gas. The object being disrupted can have gas, so there's star formation in the rings. But all the rings, even the resonance rings, can be dominated by star formation. And the differences between them, I think, is I don't know how well studied they are, but in resonance ring galaxies, if they're resonances, is extremely well organized, very well organized star formation. In collisional or polar rings, it's not so organized. Star formation rates, I'm not sure, but you get high star formation in a collisional ring galaxy. In some, and others, it may not be as much, but there's star formation. But they all have their own characteristics. But the resonance ring, or the objects that could be resonance rings, are very well organized, interesting patterns. You know, the H2 regions know the shape of the ring, that type of thing. That's organization. It's amazing. So there are differences in their characteristics. Yes.
I have a question about the shell galaxies.
Shells, yes.
Yeah. How do we morphologically identify the shells with the?
Pardon?
How do we morphologically identify the shells from the stellar halos? Like both of them are having a similar morphological shape and extent also.
The conventional way of recognizing shells, I mean, there's a variety of different topologies. The most obvious ones is you kind of have the major axis of the elliptical, and you see a sharp edge here, and the other side, further out, a sharp edge there, and on this side. They kind of interleave, they alternate, and they're recognizable partly by that. There's somewhere the shells are all around, and the pictures just really, they're in those pictures, but the way, maybe I shouldn't display galaxies as positives. Maybe I should use negatives, because they just don't display as positives as well. Or maybe if you're a little more darker, you'll be able to see them. But there are the different kinds, and as far as I can tell, they're easily distinguished, but from other characteristics. There's a whole catalog of them that Malin and Carter made in the early 80s. And I think they're distinguishable, but they're a class of interacting system.
If I can have a comment about the earlier question about the future UV missions, there's actually a Russian mission which is planned for a launch in 2015, and they plan to launch a 170 centimeter UV telescope. Now, whether that goes ahead or not, and when it's going to be launched is a different point. But there is it's called World Space Observatory UV, and I think Spain and Germany are actually taking part in design of some of the experiments. So, is anybody here actually working on that? I guess not. But yeah, this observatory should be up eventually, and fingers crossed, because that would be quite an interesting one. They hope to reach similar resolutions to Hubble.
Mm-hmm. Okay. Yes.
Hi. In the galaxies with the counterwinding spiral arms,
yes.
Can you see if they correspond to the thin and the thick disk, or are they actually just within the disk component and move through each other?
There's only two examples. I mean, two non-barred examples, and neither one is inclined enough to tell. But I don't really know. But the main leading arm galaxy, NGC 4622, has a very large bulge, and I don't know. I don't know if those arms are in the same plane. I mean, there aren't enough to say. But those arms may not. The outer arms may not be leading. Maybe it needs more work. But if you use the standard method, they look like it, and I think they're in the same plane. But there's only two. And the other ones are barred galaxies, where you have a twisted, skewed bar. It skews leading, and that's rare too. And that's another issue: is the shapes of bars. Apart from their boxiness, they might have a little bit of skewness that could be leading, and is in some cases.
Anybody else? Don't worry, John. We'll have that discussion at some point. You're still here for another week.
Just an announcement before we leave for coffee. We need Katie Alatalo, Daniela Berg, Silvia Ramos, Joel Rodiger, Elisa Portulari, Williams Hummel, Mike Williams, Jesse and Sandy, and Bursu Beigut to go to the registration desk to talk to Lourdes. All right? So let's go for coffee and be back here at 12:15.